So far, we've talked about expressing the strength of an acid, so how much that acidic proton dissociates. In terms of K or Ka, the acid dissociation constant. Um, and we have another way of expressing that, similar to the way we track the acidity of a solution with the concentration of a hydronium ion, but we tend to report that as pH. We also track the strength of an acid with then Ka values, but we're going to tend to report those as pKa values. Again, I think the logic behind this more than anything else is that it is annoying to write out values in scientific notation, and it's nice to then put them on a logarithmic scale to get a smaller range of numbers. I don't know. Um, so pKa is going to that P, right? If you haven't noticed, the theme of this series of lectures is like, let's just take the negative log of something. And the little p before something is saying, I'm taking the negative log of it. So pKa means the negative log of your Ka. And so we could also write this as the opposite. We could say that the Ka is equal to the negative log, or sorry, 10 to the negative pKa. And these are just algebraically equivalent. And so we can report that pKa in a table. And oftentimes, if you look up like how acidic is blah, 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 you'll find a pKa value listed. And so we have some examples here. Let's highlight the ones that are extremely strong acids. So hydroiodic acid, hydrobromic acid, hydrochloric, sulfuric acid, these are all really strong acids right here. And look at their pKa values, right? Their pKa values are all negative values. That's because the Ka is a larger number, and taking the negative log of it is going to give us this negative value. And so these are our strong acids. So the lower the pKa value, the stronger the acid, especially if it's a negative value then, right? Now, nitric acid too, I would say, is a strong acid. Um, hydronium ion, is kind of like the bottom of it. So I guess those are slightly different. Nitric acid isn't as strong as it is in my head, apparently. Um, but then let's look at a few that are weak acids down here. So here are some of our weak acids. Things like trifluoroacetic acid or oxalic acid or acetic acid, they all have positive numbers for their pKa values. And again, the lower that number, then it's the larger the Ka value, which means the stronger the acid. And so overall, you can just take away that the lower that pKa is, the stronger the acid. So let's go back to a previous example that we talked about earlier when we were talking about structural features of acids and how to recognize one that's strong or not. So we had looked at this example to kind of play around with these requirements that we had and find something that was kind of a bit more challenging. That we had oxo acid, a carboxylic acid, where we had a carbon for our X value, and it was bonded to one oxygen in both of these cases. But in one, it was a double bond, and the other was a single bond with then another hydrogen attached to that oxygen. And we talked about resonance stabilization of the conjugate base, really influencing which one was more acidic than the other. And at the time, we just said that the formic acid on the left was more acidic and than the other one. And when I did that, what I did is I just looked these values up. And granted, for the methane diol on the right, that one is a theoretical value that came out of a calculation. But comparing these two, they're pretty different, right? And so it's this lower pKa value right here that tells me that this is a more acidic or a stronger acid. How about we do that? A stronger acid. Which tells me that this is a more acidic hydrogen. Now, this isn't a strong acid, right? It's a weak acid because it's going to have a Ka value less than 1. It means it will favor reactants. It has a positive pKa. And that tells me, hey, this is probably a weak acid. Although comparing these two allows me to decide which one is the stronger of the two. And so that lower pKa value tells me that my stronger acid is the formic acid. Let's look at an example here. We are continuing this example of our hydrocyanic acid. And we've looked at the pH of a zero point 0.5 molar solution, and we've calculated its Ka from equilibrium constants. And so we know that it has a Ka of 4.8 times 10 to the negative 10. So what would the pKa of this be? Let's find out. So remember, pKa is just going to be the negative log of the Ka value. So this will be the negative log of our 4.8 times 10 to the negative 10. So I just plug that into my calculator and I get a value that is 9.3. So pretty big compared to something like -9, right? And so this tells me it's a very weak acid.